it's now 10 o'clock, so I'm going to begin with my slides. And please be free to put your questions in the chat. There'll be moderators there to answer them, and I'll try to keep the chat open so I can go back and touch any topics I didn't explain thoroughly. Okay, so we're going to start now with our exam review. Can everyone see the slides? Just want to make sure. Okay. All right, good. We're getting some responses. Okay, so the first section is going to be about chemical reactions. So this is going to deal with halogenation. Yeah, okay, yes, Lee, we're going to send out the packets. We'll send out the packets and these slides after the exam review is over. So first, we're going to do chemical reactions, which involves transition states and bromination and halogenation. Then we're going to do as substitution, and then last section is going to be elimination alkenes. Back one. All right, so halogenation is one of the first reactions we learned. So this is where we substitute the halogen for hydrogen utilizing a radical. So this is often seen as, we'll see it as involving Br2 and Hb, which means light or energy. So this will be used to break apart the halogen into radicals, and then this can react with our original molecule. So there's going to be 3 steps involved. First is going to be the initiation or the creation of that radical. So first what happens is the bond between them breaks and gives a radical to each halide. We get 2 bromine radicals. Propagation involves the formation of the radical on the second product. So if we have something like this, the bromine radical comes near, and again we'll see another bond breaking, because radicals need electrons to form bonds. Only one pair of electrons. So they would like to form the bond to make the 2. And as you can see, I'm doing half arrows because it indicates only one electron is moving. And so where does this other electron go, you ask? This will move back onto here. Now your product will be this. Sorry. It'll be a radical and an HBr. And so this will keep continuing and going on, but then eventually we'll run out of products. And so the last thing that'll happen is you will have this radical. We'll have this termination step. So now the radical on the carbon and the radical on bromine are going to come together. And now we get this bromine product. Okay? That's initiation, propagation, and termination. And so now we can talk about bond dissociation energy, which I'll go into more detail later. But essentially, it's the energy we need to break apart the bonds to make the radicals. So we'll see how they can depend on radical stability. All right, so there's 2 types of halogenations we specifically go over in class. We have chlorination and bromination. So as you might remember, chlorination gets more products because it's less selective. And bromination is the selective one, right? That's why questions will mostly ask you about bromination, because you can only get one product. So now something you might not know, which is less familiar, is that chlorination is an exothermic product, while bromination is endothermic. So this can be used to explain why bromination is more selective than chlorination. But keep in mind, there might be questions that ask you to draw a reaction diagram for chlorination and bromination. They don't have to be too specific, but you have to get the key points here, which is that chlorination is exothermic, bromination is endothermic. All right, are we good so far? Check in the chat. That's good. Okay, so now we're going to move on to the Hammond postulate. So we can say the reason that bromination selectivity is greater, because bromination really only gives one product, is because at the transition states between one reactant versus the other. So let's say if I had a bromination product like this or this. Chlorination of two. So that would mean if chlorination is involved in 2 steps. I think the bromination one should also have 2 steps. So this diagram looks like it only showed one. Can one of the moderators fact check me on that? But yes, back to the Hammond postulate. So between bromination products, between these two, the energy between the differences is far greater than chlorination. Chlorination can say, oh, I'm going to make the left product and also the right product and any other products in between. So, but bromination is selective. It's going to say, well, this one is much more favorable energy than this product here. So I'm going to selectively only choose the secondary radical. So because chlorination is also exothermic, its transitions, sorry, I should say endothermic. Because chlorination is also endothermic, wait, no, sorry, it's endothermic. Yes, sorry, okay, I'm right. So because chlorination is exothermic, its transition state is more closely related to the reactants. So exothermic graphs look like this, right? So you see here that the transition state is closer to this side over here, which is going to be the reactants. So this is a basis for the Hammond postulate. So it says related species that are closer in energy are also closer in structure. So the transition state resembles the closest stable species. And this can be used to explain why bromination is more selective than chlorination. Because the transition state resembles the final product, it's not going to be as stable to choose among many different reactants. It's going to want to pick one and go all the way through that product. That's a Hammond postulate. All right. So now we're going to move back to bond dissociation energy. So this is the energy required to break a chemical bond in a homolytic fashion. So that's homolytic fashion. It's like this, where we broke it apart in the initiation step. So this is part of propagation involving the formation of radicals. We're going to break the hydrogen off and replace it with a radical. So on the test, they can ask you to rank by bond dissociation energy. This is going to be inversely related to radical stability. So the more stable the radical is, it's not going to take a lot of energy to swap it out, essentially. But if it's an unstable radical, it's going to take more energy to even put that radical in the first place. That's why bond dissociation energy is inversely related to radical stability. That's a key point here. On the test, they can ask you to rank by bond dissociation energy. So what you need to do is rank by radical stability and flip those numbers. Because as BDE goes up, radical stability goes down. And so now we're going to look at some different hydrogens that are different from stability. So we have the allylic and benzylic hydrogens. And we know that these are resonance stabilized. So they're going to have extremely stable radicals, which means a lower bond dissociation energy. But be careful not to get confused with vinylic hydrogens. So although allylic and vinylic hydrogens look the same, the difference is this hydrogen here is going to be directly on the double bond. So when we remove that hydrogen and place a radical, it's an extremely unstable radical. And it's going to result in a high bond dissociation energy. So the same thing here is on the benzylic, right? We don't want to remove this hydrogen here because it's also on a double bond. And removing that will break the resonance and result in a high bond dissociation energy. Yes, they would, because we can say benzylic radicals are more stable than tertiary radicals. So therefore, they would have lower BDE than tertiary. Okay, so now we're going to move on to some reactive intermediates. So we've gone over radical stability in this section. We're also going to introduce carbocation. So we see that the two have the same stability ranking. So why is that? So we can say because a radical is essentially one part of a lone pair. So it's sort of like this radical is missing electrons. In the same way, a carbocation is a positive charge that has less electrons than it used to be. That's why these two rankings are going to be pretty similar because they're both missing electrons. So that's why tertiary, let's look at tertiary over here. That's why this is going to be the most stable carbocation and radical because of how the methyl groups are providing electron density towards the radical. The more methyl groups you have, the more electron density, the more stable the carbocation and free radical. Okay, so for those two, it goes CH3, primary, secondary, and tertiary. However, for carboanion, anions are negative charges and that they're going to have extra electrons than their normal counterparts because of the negative charge. Electrons are negatively charged. So what we can say is that we don't want more electron density added towards it. It has too much and we don't want to push more into it. That's why CH3, it goes CH3, primary, secondary. Sorry, I guess it's just it goes tertiary, secondary, primary, CH3. Because the less methyl groups we have, the less donating electrons. So that's why carboanions are more stable when there's less electron density. So now we're going to look at two other factors to consider with these reactive intermediate stabilities. So we have resonance and induction. So we know that resonance will stabilize all reactive intermediates, and it's the strongest stabilizing factor to consider first. So like someone asked in the chat before, yes, a benzoic will be more stable than a tertiary. Both will be more stable for the carbocation, carboanion, and the free radical. Because resonance will make it so that the charge is spread apart instead of localized in one specific spot. So resonance will increase stability for all three reactive intermediates. And so the second one is going to be inductive effect. So depending on the group, it will either stabilize or destabilize the reactive group. We have two types of inductive effects. We're going to have electron withdrawing or electron donating. So withdrawing groups are going to be your halogens, carbonyls, CN, NO2. So we know halogens will have higher electronegativity, and so what they're going to do is electronegativity means they're going to take away electron density towards it. So this is an electron withdrawing group. And we can also say the same thing for carbonyl groups like this. So if you see double bonds with nitrogen, double bonds are going to be taking away electron density from the groups nearby because the double bonds, there's electron deficient areas, and so they're going to have electronegativity to grab electrons. So with donating groups, however, these have electron pairs or free lone pairs that they can donate, or they themselves are donating groups. So we know methyl groups, ethers look like this, guys. Ethers, hydroxyl, amine. So these all have free lone pairs to donate. Now, considering these two groups, let's look at what affects radical and carbocation. So because radicals and carbocations are electron deficient, as we said before, they would benefit from electron donating groups like methyl or ether groups. But on the other hand, carboanions are electron rich, so they benefit from electron withdrawing groups. So you would commonly see this group right here, the CF3 group. So this is just a carbon with 3 fluorines attached. This is a really good inductive effect or carboanions. But if it was a carbocation, this would decrease stability because it's sort of like we have a carbocation that's deficient in electrons, and now we're going to draw more electrons from it, making it more deficient. That's going to decrease stability. So the key thing here is radicals and carbocations benefit from ethyl or hydroxyl or ether groups, while carboanions benefit from halogens or carbonyls. Yes, Michelle. The carbonyl can also benefit through resonance too. But I'm sort of taking it as if it wasn't resonance considering. Like there's no factor to be resonance stabilized. How would a carbonyl group withdraw electron? Okay, so that's good. That's the first half about chemical reactions. So now we're going to move on to nucleophilic substitution. So the basic term is this is an attack of a nucleophile to electrophilic carbon and a loss of a leaving group. Take some water. Okay, so first we're going to go over SN2. So it's called SN2 because there's two reactants in the rate law. We have the substrate and the nucleophile to consider. That's why it's called SN2. Another thing is that SN2 is a concerted reaction. So if you remember, concerted means one-step reaction. So the nucleophile will attack and the leaving group will also leave at the same time. Okay. That's why it's a concerted reaction. And it's going to be the backward attack of a strong nucleophile and leaving group. So we're going to go over 5 factors to consider when we're doing questions that involve SN2 and how to determine between this and something like E2. So we have nucleophilic strength, substrate, solvent. Oh, wow, you really can't see that. Okay, I think the slides will be better. That says leaving group. Leaving group and stereochemistry. So the first section is about nucleophilic strength. So based on the table of common nucleophiles, SN2 will only involve strong nucleophiles. So I'm not sure, they might have given you the same table, but when I was taking OChem, there was this table that listed the strong nucleophiles, strong bases, weak nucleophiles, strong bases, like that. If they haven't given you that one, I'll see if I can find it when it's Tyler's session. Put it in the chat. But so SN2 will only involve strong nucleophiles. So nucleophilicity can often be mistaken for basicity, but nucleophilicity involves the attack and not the stability of the negative charge. Now, a key thing here is that a negatively charged nucleophile will automatically be stronger than a neutral charge. So there are neutral charged nucleophiles that are just as strong, but if it's negatively charged, it's going to have that excess to be able to attack with. And so let's go with trends here. So we have a periodic table here. So as we go from left to right, nucleophilicity will decrease because when we have a more electronegativity, that's going to mean that the nucleophile doesn't want to donate its electrons. So that's going to decrease as we go left to right. And as we go from top to bottom, it's going to increase because when we have larger atoms, the negative charge is going to spread out more. It's going to lead to more bonding because we can have the large group overlap with the leaving group electrophile area. The larger the nucleophile, the better the nucleophilicity. Okay, yes. I will repeat the periodic trend. So yes, right here. So yes. So we're going to say increasing nucleophiles. We're going to go left and down. That's going to be increasing nucleophilicity. So if you remember the acronym, I remember it was on peer tutoring walls before, but it goes B-E-A-N. Yeah, bean. Good. So yeah, you see how basicity is Basicity is different because basicity actually decreases as you increase the size. Because it's more polarizable means it's a weaker base. So yeah, remember being. You draw it in a clockwise manner going from the top. So nucleophilicity is down here. Okay. So now let's talk about resonance. So resonance most of the time actually will help basicity and electrophiles, but in this case, it's going to make it a worse nucleophile. Because as we remember before, resonance stabilizes charges and radicals, right? It makes it spread out so that it's more stable and it can exist on its own. Yes, Tyler will have it fully drawn out in the future. So with the resonance, what happens is because we're spreading out the charge, it's going to actually make it a worse nucleophile. Because think about it, nucleophiles want electron density concentrated in one area because they're going to be attacking an electrophile. But if it's spread out, they can't do it as efficiently. That's why resonance will actually create worse nucleophiles. Now, one other thing to consider that's special for nucleophiles is steric hindrance. This is specific to SN2 because we remember SN2 is a concerted reaction. So if there's a big nucleophile, it's not going to be able to reach the site effectively. Right, so think about it. Let me draw something out. If you have the leaving group here, and you want the nucleophile to attack, if it's crowded out right here, or this nucleophile is too big, then it can't reach the site effectively, and it's going to be a slow reaction. So that's why we want nucleophiles to be sort of small, right? So you can say you may look at this and think it's a good nucleophile, but because of this steric hindrance on the back right here, this terbutyl group, because of that steric hindrance, we're going to say that it's a bad nucleophile because it's sterically hindered by a one-step reaction. Okay, everyone get that? So takeaway here is nucleophile strength increases to the left and down. We want small nucleophiles. Yes, exactly. The atom can be big because the atom's the one attacking. So let me address biasable effects again. So because we want the atom big so that when it reaches that area with the leaving group, it's going to overlap with the region and it's going to facilitate better bonding. It's going to be more polarizable. That's what we say. So we want the atom to be big, but if the rest of the molecule is really also big, then the atom can't reach that electrophilic region. So that's why the atom should be big, molecule should be small. Okay, so now we're going to talk about leaving group and the substrate. So because the nucleophile attacks on the backside, the substrate cannot be sterically hindered by bulky groups. So this is once again the same thing we're talking about. So just like the nucleophile can't be sterically hindered if it's too bulky, the substrate cannot also be sterically hindered. So we're going to say methyl goes from methyl first, primary, secondary. And there's going to be a huge gap between tertiary. So oftentimes we don't even consider tertiary for SN2 just because of how weak or how slow the rate of reaction is going to be. So tertiary for SN2 will have extremely slow rate and should not occur. Now, there's going to be another case where if you see a carbon next to a quaternary carbon, SN2 will definitely not occur. So it's going to be right here. So this bromine it looks like it's on a secondary position, which should work. However, because it's next to a quaternary carbon, so quaternary carbon means it has 4 bonds coming out of it. So 1, 2, 3, 4. Because it has 4 carbon bonds, it's a quaternary carbon, and therefore we can rank this as 5. It's going to be the least, it's going to have the slowest rate of SN2. Now, for leaving groups, what we consider is what a good leaving group is when it leaves, it's going to be unreactive, right? Because if we get a reactive leaving group, that's going to take a lot of energy. So we want this leaving group to be stable, it can be fine on its own. And so that's why halogens are a good leaving group, because halogens have a lot of electron density and they're pretty much stabilized with a negative charge. Because when bromine leaves, it's going to be bromine minus. And halogens can actually take the negative charge and spread it over, because they're large and electronegative, they can spread it over their atom. So they're pretty good on their own. Another good leaving group is water. And we're going to see in the future how to make hydroxyl groups like OH a good leaving group, such as water. So with questions, you should consider the leaving group rank, but always rank by the substrate first. So what I would do is if there's an SN2 question about the substrate, I would rank them by primary or secondary. And then when I have to make a choice between two secondaries, I would now look at the leaving group. And you're going to see a lot of this practice in our practice problems during our breakout room session. Okay. I don't know why it's spread out weird like that. So the next two parts are going to be solvent and the stereochemistry. So for our solvent, nucleophiles and alkyl halides are polar. So we know they need a polar solvent, right? Like dissolves like. So polar dissolves polar. Polar solvents can come into two different forms. They can be protic, which means an acidic hydrogen. So this is a hydrogen where a lot of the electron density has been taken away, so it can leave as a positive charge. So OH, water, NH3, those are acidic, those contain protic, those are protic solvents, as you can say. A product means no acidic hydrogen, so CH3CN. Now don't get confused with the CH3. So even though it looks like there's a hydrogen, that isn't an acidic hydrogen, right? It's just connected to a carbon. So be careful about the difference between acidic hydrogens and normal hydrogens. A product will have no acidic hydrogens. Okay? Now, for SN2, the nucleophile will attract the acidic hydrogen, which means that we're essentially using the negative charge to attack something else. We're not attacking the leaving group. So we don't want this secondary reaction to happen. So that's why we're getting polar aprotic solvents like DMF, PHC, CH3CN. These all are aprotic, and so they're going to increase the rate of SN2. That doesn't mean that with polar solvent, polar protic, it doesn't mean that it's not going to happen. It's just going to be slower than if it was with aprotic. Now let's talk about stereochemistry. So if you remember, because of the backside attack, the nature of SN2 will cause an inversion of configuration. So this can cause something to go from R to S, or whichever way you start with. Yes, this recording will be posted later too. So this is called the Walden inversion. So the Walden inversion is basically when you just switch the arrows, right? You see in my example, I have iodine on a wedge. We have CH3SH attacking from the back, and now the sulfur is on a dash, right? That's the inversion of stereochemistry we see for SN2. So this is often where points are missed. I guess since your tests are multiple choice, maybe it'll be easier, but be careful. Be sure to look out for this inversion of stereochemistry. Okay. Okay, so we can also, let me draw this out. So we can also see this inversion of stereochemistry with let's see, CH3. You can see it with Fisher projections too. So if I was to attack this with a nucleophile, what you need to do with a Fisher projection is simply flip the sides everything is on. So it goes like CH3, and now the nucleophile is there. So this will be the inversion of stereochemistry. You can also see it for Newman projections where you have something like this, and it's going to be flipped. You can now form you'll swap one side. And so the nucleophile will be on that side, and now CH3 is here. Actually, CH3SH, the thiol group is actually going to be a strong nucleophile. And remember, I included a polar protic solvent, but that doesn't mean the nuclear SN2 can't happen. It's still going to happen, but it's going to be slower than if I included DMF or something. But yeah, CH3SH is actually a strong nucleophile. Yes, we can flip, because it's only attacking that specific one, if you only flip the BR CH3, that will create the inversion of stereochemistry. If you flip everything else too, it'll just be like the same molecule, right? Because you flipped everything on the mirror plane. Deprotonation happens with all the molecules. It's essentially what happens is we have, so over here you can say it was SH like this, but there was a positive charge. And so a different acid, this is called acid workup. And so what happens is an acid here can come and grab the hydrogen, and so it's going to remove the positive charge away. This can happen with most reactants with extra hydrogen. It's not exclusive to SN2. Okay. So let me erase something and let me try and explain. Let me explain the Newman projection one again. If we have the Newman projection like this, so if we want to flip the stereochemistry because it's being attacked by a nucleophile, what we can do is we can put now the nucleophile on this side and keep the bottom the same like that, right? So we're just going to swap the top two positions like this. And that'll create the inversion of stereochemistry. So that's how on a Newman projection you can keep it the same way and swap the stereochemistry. If you want to do it the long way, you can also draw out the original molecule and do that. That's not a wrong way to do it. But this is, I guess, a shortcut to switch the stereochemistry on a Newman projection. Okay, so we've finished talking about SN2, so we're going to move on to SN1. So SN1 is a nucleophilic substitution, but it's going to involve a weak nucleophile in 2 steps. So this is not a concerted reaction as we learned before SN2. This is a 2-step process and it's going to involve a carbocation intermediate. So if you remember stability from before, we said carbocations are stable from tertiary, secondary, primary CH3, right? So in this case, we're going to determine the SN1 step, the rate of reaction based on the stability of the carbocation. That's going to be the most important factor here. So we're going to use a polar solvent this time, but in this case, a polar protic solvent is best because it can solvate both ions through hydrogen bonding. Because we now have a carbocation, we want a solvent that can basically reduce the positive charge to make it more stable. Now, SN1 doesn't involve only the backside attack. It can attack from either side, so we're going to call it a racemic mixture. Racemic mixtures have equal proportions of each enantiomer. So it's going to essentially, you can say 50, 50, R, and S, right? If you had 2 forms of it. That's what a racemic mixture is. Now, I'm going to go, there's different ways we can actually create a carbocation if we needed to for the SN1 attack. So we can use AgNO3 to leave behind a carbocation. Let me see if I explained it here. I didn't. Let me go over Ag. So if you remember, we said a primary carbocation isn't stable. So if we had something like this, if we had Br like this, right? if we did the SN1, it would form a primary carbon cation, which isn't stable. No, but the way we can work around this is if we use AgNO3, the AgNO3 is soluble, so split into silver ions and nitrate. The silver can grab the halogen, become insoluble, and now leave in turn a carbocation. So this can be used for the SN1 reaction if we need to get a primary carbocation. This will be explained more in Tyler's lecture, I think. So don't worry if you didn't get it this time right here. Okay, so for SN1, because of carbocation, there's also going to be different rearrangements we can have. So let's go over the process to do rearrangements. So essentially what you want to do is you want to consider 1, 2, and then 3. Because hydride shifts are the easiest to do, you want to consider this first before a methyl shift. So we have a hydride shift, which is where the hydrogen shifts over and the carbocation is moved. Right, it's pretty simple enough. So you're gonna look at the neighbors. You're gonna see that there's a hydrogen, and so the carbocation can move. And this doesn't when you draw it out without the hydrogen, it doesn't look like anything really happened. It looks like the carbocation just moved, right? Because not much changes. Methyl shifts. If there's no neighboring hydrogen, we can actually move a methyl group up to move the carbocation down. So look for wherever the bond broke initially. Because the bond broke at this position here, that's where our new positive charge is going to be. The final step is the ring expansion. So an unstable ring, such as a 4-carbon ring, like cyclopropane, will look to expand to create a bit larger ring because when you're that small of a ring, it's not going to be as stable as if you could get larger. So in this case, the 4-carbon ring is going to break one of the ring edges apart and attach it up there so that it can now form a 5-carbon ring. And you can see where you actually broke apart this bond right here because you sort of broke it at that edge and formed it at the top. So that's where where's our new carbocation is going to form. Look for the position where the bond is essentially breaking. That's where our carbocation is going to form. Now, something else we can talk about is making alcohol a better leaving group. So as we said before, leaving groups want to be stable. If you remember, alcohol is going to be OH, but if it leaves, it's going to be OH minus. Yes, let me go back to the previous slide. What thing you wanted me to go over again? Oh, okay. So back to the alcohol discussion. So it will form OH minus, and we know that's actually a strong base. So we need to make this more stable. There's a few different ways. If you have alcohol, you can make it a good leaving group. The first common way is tosylation. So this will convert alcohol into a better leaving group using tosyl chloride, TSCO. So what it looks like is you can have your OH here, react with TSCl, and this will form OTS like that. And then you can react this with a nucleophile. And now it will actually now you see the OH left as a better leaving group. Now a different way we can change the OH group. This isn't leaving group, but I thought it seemed important for the discussion. It seemed pretty similar. So if we use NaH, this involves the hydride ion. This is H minus. So H minus is a strong base. So what happens is this is going to remove a hydrogen from the hydroxyl group and actually make it a good nucleophile. So we have OH here. If we react with NaH, now we get O minus. And we remember O minus is actually going to be a good nucleophile, unlike OH, which is a weak nucleophile. So this can be used for intramolecular SN2 reactions. So I'm going to go over that in the next slide. This is how we create OH into a better nucleophile using sodium hydride. And now the last thing is we can use an acid to create OH into water, which is a good leaving group. So using an acid such as HCl or HBr will abstract another hydrogen to the alcohol from the alcohol. The alcohol is going to abstract the hydrogen from the acid to create water, which is a stable leaving group. So if you look down here, you can see that the alcohol is going to take a hydrogen from the HBr because this is acidic and a partial positive, so it's a good electrophile. And so now you're left with OH2 with a positive charge. And so when it leaves, it's actually just going to become H2O. So to summarize, to make it a good leaving group, we can use tosylation and acids. To make it a better nucleophile, we can use sodium hydride. And so, yes, the acid has to be strong. If it's a weak acid, it's not going to be, the OH is not going to be able to take away the hydrogen. So strong acids like HCl, HBr, HI, think of those acids. There's a rule with H2SO4 and H3PO4 that makes them want to do E2 more. That's a little more complicated. I'm not exactly sure about the mechanism. But just think about strong acids like HI, HCl. Okay, so the last thing I want to go over is, yes, Tyler explains how H2SO4 works with alcohols. So in this case, HI and HCl would be good for SN2, then H2SO4 would be good for E2. Now the last thing I want to go over in my section is the intramolecular SN2. So if we have something like this, 1, 2, OH. Right. And now let's say I react it with sodium hydride. Now we're going to form O minus like this. And so what happens is we have a leaving group here, we have a nucleophile right here. So we can actually have an attack from the nucleophile onto the same molecule like this. This is called the intramolecular SN2. Because it's a nucleophile and a leaving group in the same molecule, it can attack itself. And we formed the O minus because of sodium hydride, right? I can go back to that slide after I finish. But sodium hydride, essentially, we can say H minus takes the hydrogen here and creates a negative charge. That's using sodium hydride, which is going to form a better nucleophile, like in the slide before. And so our final product will look like this. So what I do for this is I count the number of carbons after the O to figure out how many carbons are in my ring. We have 1, 2, 3, 4, 5 carbons. So this is going to be a 5-carbon ring. It's going to have 5 carbons in the ring, including the oxygen. So it's actually going to be 6. It's going to look like a 6-carbon ring. So you see now we have 1, 2, 3, 4, 5. Did I do that wrong? Yeah, in this ring formation, it's going to be an SN2. Okay, sorry, I did a 7-carbon ring again. Ignore that. Let me redo that one again. Yeah, so as I said before, it's going to be 5 carbons plus the oxygen, so it's going to look like a 6-carbon ring. Right, so this has 5 carbons. It looks like a 6-carbon ring. So it's 1, 2, 3, 4, 5. And then the oxygen will be the 6th. Sorry, I drew the second one wrong. That was actually a 7-carbon ring. So yeah, so that's how I do the. What it became a ring because of this intramolecular SN2, right? This O minus is attacking the same molecule. Yes, it will form. Yeah, most of the time, yeah, intramolecular SN2 will form the ring because you're attacking itself. It's going to close in on itself to form the ring. Okay. So that's the intramolecular SN2. So did anyone have any more questions about this section? It seems like some people were confused about sodium hydride. Let me go back to that slide. Sodium hydride's here. This molecule right here. So I said before, it's H minus, which is a strong base. So it's actually going to take away a hydrogen. And make it into just O minus. The strong base will take away the acidic hydrogen from OH and make it just O minus. Okay, so that's everything with my section. Does anyone else have any more questions about this? Yes, we're still going to go over. I just finished my section. And yes, NaH usually only seen for SN2 because it's making the nucleophile, right? So we want to make the nucleophile for SN2. We don't want to make it for E2. And the last slide should be a 6-numbered ring. Yes, it should be 6-numbered because I drew it wrong the first time, but it should be 6-numbered. Yes, tosyl groups depronate the alcohol, making a strong leaving group. That's what tosyl chlorides do. It essentially replaces the alcohol, makes it a better leaving group. Okay, I can go back to the first. Yeah, they'll be posted later. I want to make sure Tyler has time. Okay, if we don't have any more questions, I'm going to stop my section here, and I'm going to let Tyler take over now. Tyler will be going over E and alkenes. Okay. All right. Hope you guys enjoy my slides. Tyler, take the floor.
All right. I'm going to share my slides. Let's see. Application window. Great. I think I can still access the chat if need be, but y'all can see my slides. All right, so I'm going to be going over eliminations. Where is these are for? All right, so eliminations are when our leaving group, another atom, we typically have a hydrogen, they leave the molecule with no new atoms added. So that is why we have the name elimination, because we are eliminating our leaving group and a hydrogen, forming a double bond. So the most stable product will form when possible. This is usually called the Zaitsev's rule. But typically, when you learn about eliminations and when a lot of students look to the left and the right of our leaving group, and we identify 2 possible structures from each reaction. And so a Zaitsev product is when the alkene will have the most substitutes. And we'll go over alkene stability later, but you should know that substitution increases alkene stability. And so the most stable product will be the one with the most substitutes on our alkene. And then the Hoffman product will be the other possible alkene, usually gets less substituted. Specifically, this one is the less stable product, and so it will only form if we have either a bulky base or whether or not we are blocked from forming our Zaitsev product. Eliminations are a result of basicity, and so a lot of professors stress basicity. I'm going to show you guys that you can look at basicity, but you can also just look at nucleophilicity. But definitely know that a base is it's being called a base because we are abstracting hydrogen. As the bases do, when they react with acids, they take away hydrogen. So this is bean fully drawn out. And so the way that bean works, let's see if I can. All right, so the way that bean works is we start up here, and then we go in a clockwise position. So I thought these had arrows, but this is our trend for all of our different, all these 4 periodic trends. So basicity is going to increase going up and to the left. And that's just because we want something that is not highly electrophilic, because it wants to give away those electrons, kind of like a nucleophile. But the only difference here is we want a small atom as well. And so we are going up in our periods. Electronegativity, y'all should know that it just points toward fluorine. Acidity is opposite of basicity, down and to the right. And then nucleophilicity, like Justin was saying, goes down and to the left. And that is, again, just due to really polarizability. We want a big charge, and then we don't want high electronegativity, so then we'll give it away. So now we're going to go through the E1 mechanism. So this is a unimolecular elimination. That's why it's called E1. And this really just occurs because we are only depending on our electrophile for our rate. And we'll go over that in just a second. The mechanism begins just like an SM1 reaction. So usually we do not have a strong enough nucleophile to actually attack and force the leaving group to leave. So in that case, we have to just wait for the leaving group to leave on its own. So when that happens, we do form a positive charge, or a carbocation. And with every SN1 or E1 mechanism, you have to always check for the possibility of a rearrangement. In this case, we will do a hydride shift. So the hydrogen will take its electrons and move to stabilize that positive charge. And in the process, we will create a positive charge where the hydrogen was. The next step is common. This is where it actually differentiates E1 versus SN1. But elimination reactions, they act because we have bases. They will take away an adjacent hydrogen on one of the carbons. So what we end up doing is we have our weak base, or our weak nucleophile, and we have it taking this one, which is adjacent, and then it will just take the hydrogen, leaving its electrons, and those electrons can then form this double bond here, and that's going to stabilize and eliminate this negative, or this positive charge. So note that for this, I have chosen this blue hydrogen versus a hydrogen that's on this carbon. And that is because we are looking for that Zaitsev product. When we form the double bond here, we'll have 4 substituents. And when we form the double bond here, we would have 3. Then that's our product. So that is a common feature of every elimination product. So we're always going to be forming a double bond. So the features of the E1 mechanism. So it prefers for its nucleophile or base, it prefers a weak base, but sometimes it can use a strong base, and this will be only when E2 is not possible, and also SN2 is not possible. So this is a very rare instance where you do an E1 mechanism with a strong base. But when we go over E2 and the limitations for that mechanism, I can touch on that more. So electrophile, it prefers bulky electrophiles, tertiary, secondary, and that's just to stabilize the carbocation. So our SN1 and our E1 both prefer bulky electrophiles, unlike our SN2 E2, or unlike our SN2. And that is just because the rate limiting step is that carbocation formation, and a bulky electrophile, tertiary or secondary, will just stabilize the positive charge when it forms. Our solvent, we want a polar protic solvent. Polar is just to dissolve stuff, like Justin was saying. Protic is going to stabilize our carbocation. So the whole goal of this mechanism, or like to initiate the mechanism, is just to form a stable carbocation. This is a 2-step reaction, just like SN1. First step is going to be our leaving group leaving, and the second group is going to be our base abstracting a hydrogen. E1 cannot happen on a primary. It rarely happens on a primary, just like SN1. The rate is going to only depend on the electrophile. So you don't really need to know like what K is, but for the SN1 and the E1, I like to remember that since they both have the number 1, they only depend on electrophile. Rearrangements are possible, therefore Zaitsev product is almost always achieved. So because we can rearrange, we're almost always going to form, when we form the most stable carbocation, because carbocations also like substitution, we're almost always going to form the Zaitsev product. And one important thing that Justin touched on is silver nitrate guarantees carbocation formation. So if you ever see silver nitrate, know that like I guess 99% of the time you will be going through an SN1 or an E1 mechanism. So that's a nice thing to see on the test, is because it tells you to go through the 1 mechanism. We will then go over H2SO4, unique, and this follows an E1 mechanism. So the first step of H2SO4 is to convert the alcohol into a good leaving group, because currently it's not. So what actually happens is our alcohol will attack the hydrogen on our H2SO4, and it will take it, forming water attached to our molecule. So this currently has a positive charge. It's not really, I mean, I guess it's stable, but it wants to leave at this point. So once it leaves, if it takes its electrons with it, it will actually be stable. It'll just be water. And so that is our next step. Oxygen, because it has a positive charge, will take the electrons with it, forming a positive charge in its place. Then we see that we can have a rearrangement because this is similar. This is an E1 mechanism. And this rearrangement occurs, as you can see, one of these methyl groups has shifted to move that carbocation to a more stable position. And then the most important thing is people will say, hey, this oxygen has a negative charge on it. That should be like either a strong base, strong nucleophile, something like that. But you need to remember that resonance greatly decreases our nucleophilicity. And so if you look at the structure up here, when we have a negative charge here, there's tons of resonance, like four structures that can involve the negative charge moving all around these oxygens. So because of that, this is a very weak nucleophile. In fact, the only thing it can really do at this point is act as a base. So what it will do is it will choose, again, the Zaitsev product. It will abstract the hydrogen from the more substituted direction, and it will form a double bond. So this is an important mechanism to remember because H2SO4 is one of those reactants that guarantees an E1 mechanism. In fact, I believe it's the only reactant that can like guarantee that you only do E1, you don't do SN1, and you don't do SN2, E2. All right, I'm going to make sure there's no questions. Looking good. Now we move to the E2, which is the bimolecular reaction. And again, this is really just because of its rate again. Cool. So we have a strong nucleophile or a strong base. And if you remember, our basicity increases going up and to the left. So oxygen is in that second period, and it's a little bit to the left. So this is usually considered a strong-ish base. And what we have is we have a leaving group, and then we've got 2 adjacent carbons. And what I've drawn here is there's an important rule for E2, and it is called anti-coplanar geometry. So what we need in order for this reaction to work is we need our leaving group and the hydrogen that we take to be 180 degrees apart. So how that works is I'm going to show on our next slide more about the anti-coplanar. But for this, we are locked in our positions, so there's no rotation possible. So it really only matters whether or not it's a wedge or a dash. And so know that wedges and dashes are 180 degrees apart for our consideration. And so the first step, or it's a bimolecular elimination, but it is a concerted reaction, just like SN2 is. So it will abstract the hydrogen, the hydrogen will give its electrons to form a double bond here. And then at the same time, it will kick this leaving group, or our iodine, off the molecule. And so this forms, I wrote Hofmann product. I do want to note that you could not have moved this direction because we do not have the anti-coplanar. But sometimes it helps to further think like I am forced into this Hofmann product because I did not have anti-coplanar geometry. So this will be one of the instances where you get a Hofmann product. There we go, not anti-coplanar, cannot abstract. I want to hide this. Can't hide that. Sorry. That's worse. There we go. Perfect. Sorry about that. There was something in the bottom of my screen. I don't think y'all could see it. Where my laser pointer? Sweet. So this is the anti-coplanar rule. So we know that usually wedges and dashes work on linear molecules as well, but on linear molecules, you need to remember that this can always rotate this single bond. And so even though we have a wedge and a wedge, we can rotate this molecule to place this hydrogen on a dash, and then we can form our product. So I've shown the R chirality here, and the chirality that, the chirality I was looking at is chiral center because that's what I'm going to be rotating. So I want to prove that my rotation does keep the chirality so that I'm forming the proper product. So I've shown here that our base cannot abstract this hydrogen because it is not anti-coplanar. So what we do is we rotate it. Again, it looks like I labeled this underneath bromine, but really it's this. You can see that I still have my 1, 2, and 3 because my hydrogen's on a dash. We go like this, we're going clockwise to get our chirality again. So this is the rotation that we have to do to ensure that our hydrogen is on a dash relative to our bromine. So once that occurs, we can take our base and we can abstract the hydrogen, form a double bond, and force our bromine to leave. So this is actually the structure that we get. And so this has, if you can see, the bigger groups on the same side of the double bond, whereas this product, if we had not rotated, would have had the bigger groups on opposite sides of the double bond. So we've got like a cis versus trans configuration here, ignoring the methyl. So I hope you can see that there is only one correct answer here, and it will involve you rotating a bond to get that configuration. How do you rotate it? It's kind of tricky to teach how to rotate. You really do just need to imagine, like, I'm moving my laser in a circle, but this bond is spinning. So all of these substituents, if like you stick your fingers out and twist your wrist, that's how they move. And so it takes practice, but you can try to rotate it and then check and see if your chirality is the same. And if it is, then you've rotated it correctly. That's the best way that I could say to rotate. All right, so features of the E2 mechanism. The nucleophile or base, it's going to prefer a strong base, and we're going to prefer a substituted base / nucleophile if available. So if you remember that nucleophilicity does not like substitutions on, or I shouldn't say substitutions, does not like bulkiness to its nucleophile because that will get in the way. It'll have steric hindrance of its backside attack. Our electrophile, our E2 mechanism though, it doesn't actually interact with it's not a backside attack. Instead, it acts a little bit farther away because it's only taking away hydrogen. So that's why it prefers a strong base substituted if available. The electrophile, it actually prefers bulky electrophiles, tertiary or secondary. because it wants a stable alkene. So there can be instances where you do an E2 mechanism, maybe on like a primary carbon, but those are rare, and we'll go over like differentiating in just a second. Solvent, we want polar aprotic, just like SN2, and that's just because we have a charge on our nucleophile or a base, and if it was polar protic, it would just kind of solvate and get in the way and slow down the reaction. Anticoplanar is very important. Rotate bonds if possible. That's what we did. It can force a reaction to form the Hofmann product, like our ring. We could not go to the direction we wanted to because we did not have anticoplanar. We were forced to form the Hofmann. It is a one-step reaction, concerted. And the rate, because it's E2, just like SN2, I like the number 2 because it reminds me that it depends on the nucleophile and the electrophile. So these will be questions like, if we change the concentration of methoxide, how would that change our rate? And so you can answer those questions by remembering this rate dependence. The last bullet point is bulky bases make Hofmann the preferred product. So bulky bases are really butyl. So it will be CH3, 3CO, Na. That's going to be with an O minus. Or you can see it like this. Those are the same molecule. Just don't get confused. But this is a very bulky base. And so the reason why it makes the Hofmann the preferred product is because if I drew a, I wish I could change my colors. If I drew a molecule like this, we have a clear Zaitsev product. I'm going to change to a laser. All right, we have a clear Zaitsev product in this direction because there'll be more substituted, and then a Hofmann product in this direction because it's less substituted. A bulky base is actually too big to get close enough to this hydrogen to abstract it because it's a little bit, it doesn't only work for like tertiaries, it just will prefer, because it's bulky, it will prefer the less hindered hydrogen. That will be your Hofmann product. So again, this doesn't only work for tertiary versus secondary. It can work for like secondary versus primary on another example, but just know that because it's a bulky base, it can't get close enough to the more substituted carbon as well as it could the less substituted carbon. So therefore, you will take away the less substituted hydrogen and form the Hofmann product. All right, so trends when choosing mechanisms. So there is a lot of different ways to go about choosing mechanisms, but the way that I've found is mostly easiest is to first just ask yourself the question, is the nucleophile strong? So knowing your nucleophile strengths, like knowing what affects them, is critical. And asking yourself if it's strong can almost always instantly put you in the SN2E2 versus SN1E1 category. And so once we look at the nucleophile, determine whether it's strong, we then look at the electrophile, or I like to. And so if it is a strong nucleophile and it's a primary electrophile, meaning our, let's just change. Oh no. Oh, I only went one slide. Okay, sorry. Okay, cool. So our primary. And then that, like we said, did not really prefer an E2 mechanism. It can if it's forced to. But if we do have a strong nucleophile, we usually have a strong base as well, and it will almost always lean toward SN2. If it's tertiary, we need to know that we cannot do SN2 chemistry on a tertiary carbon. So that definitely leans toward E2. If it's secondary, though, we can't actually decide just off of the electrophile whether or not it's going to proceed through either one of these mechanisms. So really, all I care about when I have a strong nucleophile is whether or not it's a secondary electrophile, because that's when I have to really look into it more. So looking into it more was when we get into the extras. So if we have a secondary electrophile, we know that stronger bases prefer eliminations, as do substituted nucleophiles. So if we have a bulky nucleophile, we will be leaning more toward the elimination product if we have a secondary. And then also stronger bases. So usually we'll see our bases being in that first period. So we could have like nitrogen minus or carbon minus or oxygen minus. And so those three basic strength increases going this way. So carbon minus is our strongest base. And that is just because of that trend, the beam trend. And then we also need to know that increases in polarizability enhance nucleophilicity and they lessen basicity at the same time. So if we have something like S minus, this is both a stronger nucleophile and a weaker base because basicity increases that way. And sulfur is lower. And so we're going opposite the trend. So if you see moving down in the periodic table on our strong nucleophiles, these prefer SN2 more times. And then lastly, branching near the leaving group, especially if it's adjacent to a carbon that is quaternary, prefer elimination. So if you remember that rule that Justin said, is that if we have a bromine there and it's adjacent to a quaternary carbon, this cannot do SN2 chemistry. So we'll pretty much force it to do E2. And this one won't even be a really fast reaction with E2 either, because there is no hydrogen on that quaternary carbon. And so our product E2 would be something like that, which isn't a very stable alkene. Now, we move to the SN1 and E1 category. So if I ask myself, is the nucleophile strong? And I say no, that will make me lean toward SN1 and E1 because both these reactions, they have to wait for the leaving group to leave on its own. They don't actually interact with the electrophile to initiate the reaction. So because of this, they prefer tertiary. They can react with secondary, and they'll least likely react with primary. They definitely can. So these rules aren't like set in stone, but these are just trends that you can recognize to help you move through the reactions. So this is all because the tertiary, secondary, primary. This is the ranking of our positive stability. Tertiary, secondary, primary is our carbocation stability. And so that's also a trend that we look for in our electrophile. Extras, I say watch for silver nitrate again because it will guarantee moving this way because you get that positive charge. So sometimes you can have a strong nucleophile if they add silver nitrate in there. Always double check for rearrangements. That is very critical. These are not very good underlines, I'm sorry. But always check for rearrangements for E1 and SN1 because they both are identical, their mechanism, up until the point where you either take away a hydrogen or you attack directly. And then this last bullet point, there will be competition between these two mechanisms. So this is something that I had to ask the professors about, how they would plan to deal with this. I hope that they've taught you in lecture that there really isn't a great way to separate the SN1 and the E1 mechanism apart because they share so many similar characteristics and the first half of their mechanism is entirely the same. So because of that, usually in a lab, we get a mixture of products, and those are our elimination and our substitution products. So that's why E1 and SN1 are not as reliable in the chemistry world. And so because of the competition, both answers can be like accepted on paper because there really isn't a way to guarantee one formation over the other, unless you have something like H2SO4. And so the exam, they said, will specify which product it wants. So the question could say, write the major substitution product for the following reaction. It won't tell you to do SN1 or SN2. It will just tell you to do substitution. Or it will say, give us the major elimination product. So again, won't tell you to do substitution or elimination, it'll just tell you to do or I guess it won't tell you to do E2 or E1. It'll just tell you to do elimination. Another way that they could specify is by not directly saying, give us the elimination product, but instead, they could only give you answer choices on your multiple choice, and all of those answer choices will have double bond. So like they could almost force you into a mechanism by not giving you any options for a substitution reaction. So again, just know that they will try and help y'all out with this SN1 and E1 competition. All right. We are now on alkenes. So this is your final chapter. Introduction to alkenes. So a pi bond is formed by overlap of unhybridized p orbitals, each with one electron. I'm going to try to move a little bit quicker because we are 11:15. The overlap forces the molecule to be planar, so we need to have this planar overlap, and so we are locked in a position. We cannot rotate. They have one sigma bond created from overlapping sp2 orbitals, and they are shorter than single bonds. So this is our, all right, this is our sigma bond, and then our pi bond is this overlap between these p orbitals. And so this is rigid, it can't rotate freely because that would break the pi bond, and it's shorter than a single bond, like a double bond shorter than a single bond. That y'all learned in Gen Chem. So pi bond geometric isomers. So the double bond prevents rotation, we have different geometric arrangements. If we have two substituents, we have cis, trans, and geminal. There's examples down here. Cis is when they're going to be on the same side of the double bond. Trans is when they're going to be on opposite sides of the double bond. Geminal is going to be when they're on the same carbon of the double bond. And know that cis, trans, geminal, these only apply to two substituent alkenes. The other nomenclature that we learn for the geometric isomers is the EZ forms. So these are only when you have greater than two substituents, so 3 or 4. And so these use the same priority scheme as chirality. What you're going to do is you're going to give the highest priority to the chain, or the atom that weighs the most or has the most mass. So this one's a rather simple. We've got straightly like different ones, but you could have extended carbon chains. So just like you would for chirality helps. So what you're supposed to do is draw an imaginary line through the double bond. We kind of do that for like cis and trans to decide what side of the double bond they're on. But for E and Z, we have to number these. And looking at this, we've got 1, 1, 2, 2. So if our highest priority is on the same side of this imaginary line, we get Z. So people remember same side, like if you swap the S's for Z's. And E is when you have highest priority, which is the ones on opposite sides of our bond. And you draw the line vertically. So yes, the textbook a lot of times draws this line vertically, but when I see that, you have to remember that you're not comparing carbon to carbon because there's no real like, wait, no, because yeah, if you draw it vertically, it never made sense to me. I always like drawing it horizontally and then just knowing that you are looking at a single carbon like you're doing chirality. If you did draw it vertically, maybe you guys can see how you can have 1 and 1 on the same side. But if you are saying the same side, you're saying that it's, again, on the same half of this double bond, the upper half or the lower half. So I think it's just better to draw your line here. And then just make sure that you are ranking based off of the same carbon. Br and Cl1. So that we are ranking kind of like chirality. So fluorine, kind of a periodic table here, but fluorine is at the top of your halogens, and then chlorine is the next row down, and then bromine is your third row down. So we're just ranking by mass. So we're looking at this one carbon. Bromine has a mass of like 79. Fluorine, I don't remember, is it 19, 17? But it's definitely lighter, and so bromine has the highest priority. Chlorine versus CH3. Chlorine is definitely heavier than a carbon, and so that gets our number 1. All right, Elements of unsaturation. So this isn't super critical for your exam. I know they probably touched on it. The only thing that I can see it helping you guys on your exam is if they gave you a chemical compound and asked you to choose like what it could be. And so this is a shortcut to find out which structures are valid. So the element of unsaturation, double bonds introduce us to elements or degrees of unsaturation. So when we're losing hydrogens from our ideal amount because of the presence of a double bond. So there's two options. They like to teach that you use this general formula, find the maximum hydrogen amount, and then you find how many hydrogens the molecule is missing, and then you divide by 2. And then this formula, you're supposed to count nitrogen as half a carbon, hydrogens as hydrogens, and you're supposed to ignore oxygen. You can look back at your slides if you choose this method. The method that I used for OCHEM 1 and OCHEM 2 was to just memorize and use the following formula. So you take your molecular formula. So let's say we had, I need to change to my pen. Let's say we had CH3, CH2, CH, C. I'm trying to make this up. Right, this doesn't. I'm bad at making stuff up on the spot. This is horrible, but if I were to accumulate this together, we would get C4, what is that? H9, and then nitrogen. And so if we plug this into our thing, we would have 2 times 4, which is 8, plus 2 is 10, plus a single nitrogen is going to be 11, minus 1, or minus all of our hydrogens, which is 9. And so we don't have any halogens. And so 10, 11 minus 9 is 2. Divide by 2, we have 1 degree of unsaturation. And so we know that this, would be a 1 degree of unsaturation. And so the possible structures based off of what I've drawn here could be this. It could be a lot of different structures, really. But just know this is where it helps you identify. So if they give you a bunch of options for how the molecule can look, you can always check to see if the octets are satisfied. You can count the whole number of hydrogens and the amount of carbons and nitrogens. Or if you know your degrees of unsaturation instantly, you can see that if we ever have a triple bond in any of our structures, that's too many degrees of unsaturation, so we can eliminate those. And then a ring and a double bond are 1 degree of unsaturation each. And so I put benzene is going to be 4 degrees of unsaturation. It's 3 double bonds, 1 ring. So these are just really if they ask you to draw or choose the proper, like which ones could be created from this molecular formula. So that's about it. Nomenclature. How are we doing on time? A little over. All right, nomenclature. So for alkenes, we use the -ene suffix instead of -ane for the main chain. You need to specify location. So write the number of the first carbon in the bond. For multiple bonds, like multiple double bonds, keep the A from the main chain and then use di, tri, tetra in front of the -ene. So this is a little bit of a confusing bullet point, but we have one example on this slide. And then cis or trans comes at the beginning of the name, just like R or S when you guys named named compounds like that. One more thing is that for a cycloalkene, we want the number 1 position to be where our alkene is. So I've started with that. This name is just going to be cyclohexene. You don't really need to specify 1 because there really is there's no substituents, first of all. And then you assume that it's in the 1 position. The double bond takes precedent in the ring, make them the 1 position. For our second structure, this one, we start by number longest, trying to give priority where to do. For this, it's going to be at the alkene. And so we know we've got 2 as our double bond. 5 is going to be pent. And so I would assume it's going to be pent, 2, then ene. So that is what it is, and I hope you can see that you do pent, dash, 2, dash, and then the -ene suffix. For this last one, we identify our longest carbon chain. We've got 7, and we number so that we give the alkene priority over alkane substituent chains. And then we have to identify. So we've got 1 double bond at 2, 1 double bond at carbon 4. We've got a methyl group at carbon 3 and a methyl group at carbon 6. And then to make things even more complicated, we have 1, 2, 3 substituents at the 1, 2, 3 substituents at the first double bond. And in the second double bond, we only have 1 and 2 substituents. So with that, oh, I didn't actually specify. I needed to. We can quickly identify. Oh, no, never mind. You can't actually do E and Z because they haven't drawn it. I'm sorry. That's why if they drew it out, crazy, like giving you the actual like stuff like that, you could choose E and Z, but because it's a linear structure, you cannot, because you don't know which side of the double bond these two are on and which side the hydrogen versus the carbon are on. So the final name is going to be 3,6 because we've got 3 and 6 for our methyls. So dimethyl. Hepta is 7, and then you have that A, like this rule. Keep the A from the main chain. Hepta, 2, 4, diene. So that's the di, and then ene. So this one's a little tricky, but it was something that they wanted us to point out. All right, so stability for our alkenes is going to be all about our heat of hydrogenation. So this is a reaction. You mix hydrogen gas with platinum with any alkene, and it will like hydrate. I don't know. It'll eliminate the alkene. It'll just destroy it. And the amount of energy that's released determines its stability. And so if there's less energy given off, then it was more stable to begin with. So that's the logic they give it. So this is just the reaction. I don't think you'll need to know the reaction coordinate diagrams, but it's just helped to kind of see it. So we can see that this is a monosubstituted alkene. It's supposed to be on laser. Monosubstituted alkene, and it's higher energy than a disubstituted alkene. And because of that, the disubstituted gives off less energy than the monosubstituted. The overall alkane stability from all of that goes, it increases our stability as we increase substituents. So mono is less than di, which is less than tri, which is less than tetra. And then in our disubstituted, we have a very narrow window of difference of stability. And it's just because the R groups, when they're forced on the same half like cis, they kind of bump into each other. So it's a little bit less favorable. And then it's unique, but geminal is actually 120 degrees apart. And it's hard to tell between cis and geminal. Like it's easy but it's hard to explain. But cis actually bumps into each other more than geminal does. And so that's because these ones are forced to be 120 degrees apart, whereas these ones are kind of more in the same direction than it would tell you. So like you can look in the book if you want to look in cis and geminal more. But geminal is more stable than cis, and then trans is the most stable of our disubstituted. That's because our R groups are far away. There is a random rule called Brett's rule, and this is just rare. I wouldn't put too much stress in this, but it's for a bridged cycloalkene. This is where you have this bridge, where you have like 2 ring systems. You can see that I'm circling 1 ring, including the bridge from this direction, 1 ring, including the bridge from this direction, and you actually kind of have a 3rd ring, which is just the blue. So if there's a double bond at one of the bridge head carbons, these are these 2 carbons, 4 and 1, and then 1 and 6. This really only shows up in ranking alkene stabilities, because if they give you something with a 6-membered ring, or like with a bunch with only 6-membered rings, or anything less than 8, this is going to be a Brent's rule violation. It's going to be very unstable. So the only stable Bridge cycle alkenes are ones where you have one 8-membered ring. So you can see that this blue ring is numbered 1 through 8. And so this is an 8-membered ring, and it says it's actually kind of stable. So usually they won't give you an 8-membered ring and then ask you to compare it, because I don't think they've actually gone over that. But they will give you Brent rule violations where these will just be very unstable. That's about it. So the last slide that I have is an additional alkene formation. So there are some alkene formation reactions. A lot of them that you'll do this unit are just E2 and E1. But there's one additional mechanism, and it's called vicinal dibromides. So it's 2 bromines on adjacent carbons. These can react with iodine, so I-, and it will create alkenes through this mechanism. So sodium iodine or potassium iodine will come and it will take away a bromine. The electrons will move, and it'll force the bromine to leave. So this kind of looks similar, like this part, to our E2 or E1 mechanism, but know that we actually have 2 bromines instead of a hydrogen and a leaving group. This forms double bond. So that is actually it. Okay, sorry about that. I don't know if it's the Wi-Fi or if it's Blackboard Collaborate. I'm not going to have my camera on because that might be slowing down my connection for some reason. Never had a problem before, but it may just be because there's you guys in here. Anyways, we are going to rank by rate of bromination on the hydrogen indicated. So if anyone wants to either hop on the microphone or send in the chat, what are we looking for, do you guys think, for this rank by rate of bromination? It has the hydrogen indicated, so it's trying to help us out there. But what are we looking for? Stability, someone said. Free radical or carbocation trend. Yeah, does anyone know that trend? Like, what's going to help us? People are saying 3, 2, 1. Yeah. So this is the trend for carbocation stability. And so they are indicating the hydrogen for us, and know that we will have something like bromine with a radical coming, and it will attack the hydrogen, forcing one of the electrons to move with that bromine bond, the other electron to come and form a radical. And so essentially what we can do is we can just put a dot at the base of every carbon that they've indicated. If they did not indicate carbons, what will we do? How do we know which location we are talking about? Anyone know that? Pick the best option. They're in the best place. Yeah. So bromine, you need to remember, is a selective reaction. Chlorine will go everywhere. Bromine is only going to form at the most stable. And so they are indicating the hydrogen here for us because we're ranking among the same compound. But if they give you different compounds each time, you would have to then choose the best carbon or the best hydrogen on each compound to take away to determine the best radical stability. Real quick, would the second one be allylic or benzylic? This one's going to be, I think, benzylic, but it's also in an allylic position because it's just one away from the. So it's not. I don't think they're going to tell you or ask you specifically which one it is. But this ranking, we know that we have 3 tertiary, greater than secondary, greater than primary, and so we can then just look at where our radicals are. So we can say that this one, the first one, has tertiary resonance or tertiary the substitution. This one is going to be secondary, but like someone said, it's going to be in a benzylic position, or we can just simply say it has a resonance. The third carbon, the third compound, is going to be primary. Our other compound is going to be tertiary, and then our last compound is secondary. So from here, we know that I should put resonance as the greatest. because anything with resonance is going to be greater than stuff without resonance. So our resonance structure is going to be number 1. And then we can look and say that primary is going to be our number 5. Secondary is going to be our number 4. We then have to compare between these two tertiary structures because they're both tertiary. But what's different between the two of them? CF3. Yeah, so Justin spoke about that in the lecture. What type of group is CF3? It's inductive effect, yeah. Anyone know what type of group that is? It's going to be electron withdrawing or electron donating? Bad for carbocation. Good. Good. We are with a withdrawing group because it's highly electronegative. So F fluorine is highly electronegative. We've got 3 of them. So there's a pull. If you ask yourself, what is our problem? We have a radical. A radical, just like a carbocation, is an atom that does not have its full number of electrons. So it's already electron deficient. If we put something right next to it that's pulling more electrons away, it's going to decrease stability. And so I'll just put like an unhappy face with that CF3. And so because of that, we're going to have 3 and then 2. So our final ranking is 3, 1, 5, 2, 4. Resonance trumps tertiary, even if the resonance is on the secondary carbon. Yes, so resonance is the best. And then usually we have to compare what our resonance actually does. So benzene is great because we've got a lot of resonance. If we just had like 1 double bond, you have to compare both forms of the resonance. So if we were to resonate, and we were just to imagine that we had like an allylic position, our other form of resonance would also be secondary. You can see that. We can continue around the ring. They're all going to be secondary, but to also look at like its resonance form if it's not like a benzene ring, because you can have 2 structures with resonance, and in order to differentiate between them, you need to look at their resonance structures. Would an electron donating group on the first one change the ranking? Yes. So technically, the electron donating groups that y'all know of are alkanes. And so bigger alkanes are going to be more electron donating. And so if there was something where there was a longer chain on this one potentially, then it could donate electron density and then stabilize. All right. So we're going to move on to number 2. So one thing about this packet is Justin and I made it really big. 1 is the most stable. Yeah, sorry. 1 is the most stable, 5 is the least stable. All right, but when Justin and I made this packet, we included a lot of problems, more than we knew we could solve with y'all in the breakout rooms. And that is because this is going to be more of like a what is it, recitation style, where I walk through the problems with y'all's input. But I'm going to leave some of these problems for y'all to do on your own. And you can compare them with the key later. And so that's just optional practice for y'all. And then also, yeah, if you want to just look at the key, you can do that. But these are going to be some questions that I leave for y'all. We're going to do the second one. It's going to be ranked by SN2 reactivity. So what do we remember about SN2 reactivity? We're looking at the electrophile. We're going to give you the worksheet, the keys, and the notes. Yep. Methyl 1, 2. Yep, 3 does not react. And we are actually ranking the electrophile. And so we don't want high substitution because it will get in our way. What we can do here is we can look at the carbon that our leaving group is on. So we can say that this one's tertiary. We can say that, no, that's secondary, my bad. This one is secondary. This one is secondary. This one's primary. I put an N. And then this one is also primary. So we are looking at this structure, and we can see that we have 3 secondaries and 2 primaries. We don't have any tertiaries because that one wouldn't be reactive toward SN2 at all. Yes, technically that is methyl. I'll tell you all that. But you can also call it, or no, yeah, it is just methyl. I'm sorry. This one is going to be our number 1, but you could also think that it's just attached to 1 carbon, and then this second structure is going to get in our way, so it's like side steric hindrance. We're at number 2 for this one. So that's how we deal with the, yes, methyl and then the primary position. Next, for the secondaries, how do you guys think that we can differentiate between these? Bulkiness, yep, that's one thing. Their neighbors, that's another great thing. Is there any structure here that is bad? The rings, yep, they're definitely bad. One of the rings is much worse than the other ring. You all know? So the third one is a square, and it's not just because it's a square. The biggest thing is that, I'm going to change my color. The biggest thing is that this one is quaternary. And if we have a quaternary carbon, then we can't do SN2 if it's adjacent to our leaving group. So that's one of those little exception rules. And so because this is secondary adjacent to a quaternary, this one is going to be almost non-reactive, and so this is going to be number 5. Then we compare for the other 2, and y'all were right. Rings do get in the way. They are considered bulky. And not just in general, but you can also look that this bromine has a primary carbon next to it, or just a methyl group next to it, sorry. And then it also has just another single chain. Whereas on the ring, we have like an extended chain on this side, and then we actually have like a tertiary group over here. So because of that, this has more steric hindrance as a whole. You definitely do need to just, this could be worse. Like if this was tertiary on both sides and this one was just a ring, then you could say that the ring is better. Does that make sense? This is all just nearby steric hindrance. But according to what we've just described, we're going to have number 3, and then we're going to have number 4. I have to go. The key will be on e-learning or emailed out. Writing's in the wrong place. All right, I'm going to unzoom. Hopefully that works. Yeah, it can be finicky sometimes. We'll have to see. Yes, they'll be either emailed out or they may be put in a link form underneath the recording of this video on YouTube. We'll figure that out, but you'll get access. Can you repeat about something being next to a tertiary? Yeah, so I was going to say that it's not always rings are worse. If we did have a structure like this, are you able to see that? This is a secondary carbon, but both positions next are tertiary. They're not quaternary, so it's not going to like 100% not happen, but they are both tertiary. So this is going to have more steric hindrance than our ring. I hope that makes sense. So it's not, just don't automatically accept that rings are worse. You do have to compare situationally. All right. So we are going to, because ring, the first neighbor is kind of like this group. It's a tertiary, but a second neighbor is secondary. You have a question? Do you want to ask it? Okay. I drew a structure with methyl instead of an O group. So that won't really matter for it, which is better for F2. I don't think they'll ask you to compare that because you don't, I mean, this will technically be really far inductive effects and I'll be pulling electron density away, which might make this a better leaving group. So I'd be leaning toward OH. I do not think they would ask you directly some this. Reactivity go down with stability, less stable, more reactive. So we don't really compare stability, it's really just steric hindrance. Rings not being necessarily worst. So you have to compare situationally. So I drew this bromine structure on the left with tertiary neighbors. And then there's a ring structure with one tertiary and one secondary neighbor. So this actually is a linear structure that's worse than our ring. So you just have to compare the neighbors. You're looking at overall steric interference. All right. We're going to skip number 3 because that's going to be carbocation stability, which is kind of like alkene stability, or which is kind of like radical stability. So we're going to skip number 3. It's also important for you all to maybe show some rearrangements for number 3. But again, the key will show that. We're going to move to number 4, 5, and 6. One thing we're going to do is we have rank by their reactivity for the E1 mechanism. This one's nice. Rank by basicity, and then rank by heat of hydrogenation. All right, so we're going to do number 4. Rank the following by the reactivity for an E1 mechanism. So just in an effort to, I mean, we have an hour, but this is a long-ish packet. How do y'all think we should write this first step? It's E1. What should our formation of carbocation stability? Perfect. So all of these, first of all, have the same exact leaving group, but we only compare leaving groups if we have the same carbocation. So I'm just going to show you guys something. For ranking by SN1 or E1 reactivity, if you're looking at the electrophile, I like to just like scribble out the leaving group, this is left, and I just put a carbocation at the base of where it was. And so you can see that we have a secondary, we have a primary, we have a secondary, and then lastly, we have a tertiary. Okay. Secondary. And so these groups that I've drawn, we have a tie here for secondary positions, but the molecules themselves are different. So it's a little bit of like a different case, but if you ever do have a similar substituents or substitution, so secondary and secondary, and you had different leaving groups, that's when you investigate leaving group ability. So something like bromine is better than chlorine, so you would choose that structure. But the first thing you rank by is carbocation stability, because the rate determining step is the carbocation leaving. Okay. So continuing off of this, we know that tertiary, or our trend for carbocation stability, is resonance greater than tertiary, greater than secondary, primary. So we don't have any resonance. And then our answer for this is just going to be tertiary is number 1. Our primary is going to be number 4. And then for the secondary positions, we have a difference here. So this one, I'm going to draw it. It looks like this, whereas this structure looks like this. So we actually do have an extra methyl group here compared to this position. You can do a hydride shift, but those aren't accounted for in the stability. The hydride shifts do not actually, those happen like you can look at the text, it'll say like, do not take hydrogen shifts or methyl shifts into account when you rank by reactivity. But you can look just on the basis of this, we will have more inductive effects from this bulkier group because we have more electron donating groups. This group does not have the 2 methyls. Instead, it has I mean, it's not 2 methyls, but you can see that this group does not have as many carbons, as many electron donating groups. So our third compound is the more stable of the 2. So I hope that makes sense. But we're going to have 2 and we're going to have 3. Again, that's just because of the inductive effect stabilizing that carbocation. I'm going to give you guys number 5 to do on your own. We're going to move on to number 6. So number 6 is heat of hydrogenation. The bulkier is more reactive. Yes. So again, that's for multiple reasons. Bulkiness doesn't really affect SN1 or E1. In fact, bulkiness stabilizes it if it can. And there is an option for a rearrangement later on in the mechanism. But bulkier just helps stabilize that carbocation. So that's why we get that answer. So this be tri-substituted greater than di-substituted. Yes. So we are just comparing by ranking by heat of hydrogenation. You need to remember that low heat equals stable, right? And then high equals unstable. And so that's slides. You can look back on that or look at the textbook. These are our rules for heat of hydrogenation. So we are just looking at alkene stability. So this one, we can say that it's di-substituted. This one is tetra. This one is di. This one is di. And then this one is tri-substituted. So we know that tetra is going to be our most stable. And so if it's our most stable, it's going to have our smallest heat of hydrogenation. So this is going to be our number 5. However, if we look at the tri, if you remember that exception rule, it's called Brett's rule. This is a bridged cyclohexane or hexene, and they're bridgehead carbons, which are here and here. And we have to remember that the rule says that unless one of the rings has 8 carbons in it, we will not have a stable double bond. And so any violation of Brent's rule is pretty much instantly going to go to the bottom because you're going to have super ring strain and you just ignore the substitution effects. And that's going to be our most unstable because this is a Brent's rule violation. This is very, it's just I don't even know if they'd be able to form this on their own. So we'll continue to rank, but we need to know that this is can you confuse how you determine di? Okay. So di, and that's not supposed to be pi. It's supposed to be a d. I don't know why I changed to capital. But this is just the substitutions. We've got 1 and 2 substituents on our alkene, so that's di. We have 1 and then 2. We have 1 and then 2. Whereas tetra is 1, 2, 3, 4. So just knowing that alkenes, they get more stable, the more substituents they have on them. All right, so continuing, we have a couple of the di options. So we need to know that rings, especially squares or triangles, these are very unfavorable geometries on their own. And if you incorporate a double bond into a square or into a triangle, or cyclobutane or cyclopropane, these will be unfavorable. So of the 3 di substituted alkenes, this cyclobutene is the least stable. And then we compare, this one is going to be trans. This one is going to be cis. So we remember that trans is more stable than cis because we have farther apart groups. So of all of them, this one's going to be number 4 because it's the second most stable. Next, we're going to have number 3. This is the third most stable. Lastly, we're going to have number 2. This is getting more toward instability because we have a ring strain and we have it's on the cyclobutene, and then this one's going to be number 1. So this is a tricky problem. That's why I wanted to do this, and that's because you have to rank by heat of halogenation. So geminal, remember, is going to be a double bond with the same carbon. And so this one is going to be cis if you want to actually give it a name. And that is another good thing to say is cycloalkenes, they're not bridged, are generally stable after like 5 carbons. I'll go over the bicyclic structure in just a second. But this is stable because it's in the cis conformation relative to the ring. So there is a cyclohexene that could be trans, and it's horrible to draw. It's actually very hard to draw. 1, 2, 3, 4, 5, 6. Yeah. So it's hard to draw. But if we locked it like this, I hope you can see. They won't show it on exam, or that they may, I guess. But the double bond is here, and you can see that it has a trans permanent geometry, and this ring does not look happy. And so you can imagine that it does need this nice ring structure in order to be stable. If it's just a alkene, and it is at least 5. All right, thank you. The review key will be posted where? I believe it will be posted as a link under, it'll either be emailed out to you guys, or it will be posted as a viewable link underneath the YouTube video, and the YouTube video will be on the Peer Tutoring YouTube channel. All right, so we're done with number 6. Oh, I needed to go over Brent's rule violation one more time. So this is number 1 because it is the least stable. So high heat of hydrogenation, we had largest is 1. High is unstable. So this is our least, because Brent's rule says that if you have a double bond that's touching one of these bridgehead carbons, the only way that it's stable is if one of the rings has at least 8 carbons. And since we have 6 carbons in all of our directions, and then I guess 5 carbons if you include the upward ring. We've got 2 5-carbon rings and 1 6-carbon ring, depending on which way you draw your circle. And this one does not have 8 in any of its rings, and so because of that, it's a Brent's rules violation, and so it will be very unstable, more unstable than if it was a cyclobutene or cyclopropene. All right, so yeah, these bicyclic compounds really should only be showing up on a ranking question. And if they do show up, I would assume they would be a violation of Brent's rule, because I don't see how you could compare a one that follows Brent's rule to the rest of the molecules easily. So I would just say that definitely count the carbons, but most of the time if they do show you a bicyclic compound, it's not going to have 8 carbons in one of the rings, and so it's going to be a violation. It has a double bond, so it's not going to be stable. All right, so we're going to move on to number 7. So the rules for this are write out the major substitution and elimination problems, then specify which mechanism the combination will prefer. So for this, I'm going to ask you guys the following questions. So if you remember my flowchart from my slides, I first asked myself, is the nucleophile strong or is it weak? And then once I answer that question, I then look at the electrophile, and then I, if needed, look further. So our nucleophile is sodium methoxide. Don't want black. The sodium methoxide is CH3O minus methoxide, and then sodium is its metal. And then we've got one bromohexane. So let's do 1, 2, 3, 4, 5. That's 6. 1, 2, 3, 4, 5, 6. Yeah. And then bromine. So these are our reactants. So is our nucleophile strong or weak? It is strong because it has a negative charge on an oxygen. And so because it's strong, I'm going to write. Because it's strong, which side, like which pair of mechanisms are we going to be examining? The ones or the twos? Yeah, so because it's strong, we're going to be examining SN2 and E2. And so it's asking for both products, major substitution and elimination products. So we're going to act like we're just going to do both of them. All right. So if we did, we would need to take, we've got a carbon, it's primary. We would need to take an adjacent hydrogen, there's only one, and it would need to abstract that hydrogen and form a double bond. So our product would look like that. For the SN2 product, we have the backside attack on that primary carbon. There is no stereochemistry here because there's two hydrogens on there, so it's not a chiral carbon. So what we are going to end up with is this. Did y'all follow both of those reactions? Or if you have a problem with any of the reactions that I do, just speak up and I can go more detail. But I don't have the space or the time as much to go over every mechanism. These are our products, and looking at these, we can't really just compare the products, but if you remember my rules, which one are you preferring here? Are we going to prefer SN2 or E2? Got some mixed answers. So what I said is that primary carbons, SN2 really loves primary carbons. And then E2 really loves tertiary carbons. And so the reason E2 loves tertiary carbons is because it'll form a more substituted alkene. If we were to look at this alkene, this would be mono substituted. So this is on the lower end of the stability for the alkene. If we look at the SN2 chemistry, we could say that this has like almost no sterics. Do they equally dislike polar protic solvents? Yes, they don't like polar protic. Because both of them involve a charged nucleophile trying to move through the solvent. But remember, solvents never actually force a reaction to go one way or another. Usually when they ask about solvents, they really ask about them. They ask about them in the context of like, if we were to change the solvent from this to this, how it would affect the rate. But solvents don't force it to go one direction or the other. You just need to know which mechanism prefers solvent. Ethanol is just our solvent, so it can have polar protic solvents even though it's SN2 and E2. put ethanol here because technically ethanol could have done SN1 and E1. But this will not act as our nucleophile in this case because we have a primary carbon and a few different factors. But sodium methoxide is our nucleophile in this case, and it will attack our leaving group. And what I've been trying to get at is that SN2 will predominate. So SN2 preferred, and this is because we have primary leaving group. And so it's because E2 doesn't really like primary that much, and that's because it's monosubstituted. It can be forced into it if we have something where we can't have SN2 because we could have like a quaternary carbon nearby or something else, but we're just looking at the primary leaving group and saying that SN2 is the preferred mechanism. Y'all have questions on this problem? If there was a quaternary, it would be E2. Yep, so I know we're changing the problem for this little example, but if we did not have that product or reactant, this would be a quaternary carbon. And so it would actually not be E2, I'm sorry. So this is a quaternary carbon, it cannot do SN2. And then because there's no hydrogen, here I should point, because there's no hydrogen here, it can't do E2 either. So what actually has to happen is it would force it to go through SM1/E. And you would have to have this group leave first, have a rearrangement, and then you could do E1/SM1. So again, it's all situational. Do you have any more questions? All right, I'm going to move to the next page. So I'm going to skip this problem and skip this problem because I want you guys to do one with that and then one solving, like decoding the words. We're going to move to this third question, or the last question for this section. We've tried to choose harder questions because so that the key should explain it pretty well. We've tried to choose slightly harder questions because if y'all can do the harder questions, you can do the easier ones. But this definitely does come with practice, and y'all still have time. Your exam is Wednesday, so practicing different problems can help you identify these trends. So for this third reaction, what does silver nitrate do? SM1E1, SM1, yep. So this guarantees our carbocation formation. So the primary is not super favorable for SN1 and E1. This will force that carbon or the chlorine to leave and will form a positive charge because we have silver nitrate. So silver nitrate definitely tells us to move to the one direction, but if we also looked at our nucleophile, we could see that it's a weak nucleophile. And so that's because it doesn't have a charge. And so with a weak nucleophile, it can rearrange, you're right, but we would lean toward SM1E1 already, but silver nitrate definitely helped us in that direction as well. So then, like any, you have a strong nucleophile, we would still, yes, because it would force that leaving group to leave. That's only because of silver nitrate. All right, but continuing off of this, we first have a hydride shift. The hydrogen here, it's going to move. hydride shift. Oh, yeah, I can do this. So that's our new location for our carbocation. It's now tertiary because we had a hydrogen move. So at this point, we have two options. E1 and then SN1. So SN1 is going to be where this attacks directly, like all substitutions. And initially, we have that hydrogen still on there, and then it's going to get abstracted. This is our answer for hydrogen. Know that, again, technically, this is not chiral because there's two methyl groups. You still could indicate wedge and dash and stuff, but they could give you an option with no wedges and no dashes to illustrate that this is a racemic mixture. Or they could give you a wedge and a dash, and then I would assume that if it would probably not indicate stereochemistry. But again, there is no right or wrong answer for stereochemistry because SN1 always results in an equal, like E1 plus its enantiomer. Continuing through the E1 mechanism though, we would choose, I mean, all the hydrogens are more or less the same. Would choose the hydrogen that I've drawn. And so we would have that mechanism. And I did it again. Sorry, but I have this structure. Both those products make sense, hopefully. And then looking at this, there actually is no preferred. So mixture E1, SN1, and then I'll remind you, test will specify which. So like, again, they'll ask, what is the major substitution? What is the major elimination problem? Or they'll only give you one answer choice, like all double bonds or no double bonds for your answer choices. So I was told from the professors that last week, that is how they imagined they would approach this. And again, I suppose it would change, but I really don't think that would change because I hope you can see that both these answers are equally correct because both will happen in solution. All right. So that can be an issue where they trick you. I'll give a very quick example. There are some times where they could give you something like this. I actually like this one. That's opposite. It looks like sodium hydride would make this O minus. The O minus with its cyclohexane ring into the nucleophile, and it would then come and attack our electrophile. So no, they're not always written above the arrow. All right, so I'm going to continue to question 8. This question, there's a lot of them, but this will be a big portion of your test where it's just straight up asking individual reactions. Yeah, in that case, the electrophile was over the arrow. So then we will have to decide which would be a better nucleophile. So the first one can't be a nucleophile. The last question that I drew, bromine is not. It's not bromine minus, so it would not be prompted to be a nucleophile. But for these questions, what I'm going to do is I'm going to have a rolling poll. So I'm going to say which mechanism. So let's do SN2, SN1, E2. All right, so y'all should be able to see this poll. And it's going to be a rolling poll, which means, or I didn't
but y'all can change your answers at any time. So we're going to talk about this first reaction, and I want y'all to look at it and then vote what you think the mechanism will be. And then when we get to the next one, I'll tell y'all to vote again, and you'll just change your answer. Okay, so this is anonymous. Y'all won't know like who's voting what. I'll give y'all just a second to look and analyze and then vote. I will specify that NaOET and metal, there has to be an ionic bond. So that should tell you that you have an O minus. And then ET is the abbreviation for methane. That's what this looks like. So it could be O, CH2, CH3. All right, so we've got a couple votes for SN2, a couple votes for E2. So it looks like y'all decided that this is a strong nucleophile. So you want to choose between SN2, E2. So that's good. And then the votes are swaying toward E2. Anyone that voted E2, someone already said it, SN can't do tertiary. So you also have to look, so if you follow that chart, first you look at the nucleophile, you decide, and y'all did it, and chose the two mechanisms. Then you look at the electrophile. So our leaving group here is tertiary. And so we said that tertiary can't do SN2, and that's true. So our only option here is E2. And so what it will do is we need to look at our bromine, because we do have the anti-coplanar rule. Our bromine is on a wedge. We want to see if we can take off of the most substituted carbon. We actually do have a hydrogen on the dash. So because we have this wedge dash relationship, we can get the Zaitsev product, which will look like that. And again, we have lost the wedge in the dash because when we have a double bond, this is forced to be planar. And so this no longer has stereochemistry. And that is our answer. BR2, this should have HV. This does not actually have a, it's not E1, E2, SM1, SN2. This is radical halogenation. And so what we're going to do is we're going to initially, after all like the initiation, propagation, we're going to take our best hydrogen. We want hydrogens that are in position with resonance. And we are going to form radicals. So let's say we form a radical here, and we form a radical here. I'm going to use a different color because I'm considering my options. These are my two. Actually, technically, there is a third up here. These are the three situations where I would have a radical formed that is resonating, like it has resonance. So these are the ones we care about the most. We then need to compare, because we're looking for the most stable. We then need to compare their resonance structures. So the red one would come down and then take one from the double bond, and then this would form a radical here. The green one would form a radical here. And the blue one, its other radical will also be here. I hope you can see that resonance pattern. But what we can see is our best possible radical is right here. And so I'm going to draw it fully out. What we're first going to do is we're going to have a radical here. And then, before the bromine reacts, it's going to resonate, forming this product, which is the most stable radical. And finally, bromine will come and attach here. You all have questions about this reaction? Okay, great. Moving on to the third reaction, y'all can vote again. Which one do you think it'll be? All right, so again, we've got a pretty even split between SN2 and E2. So y'all were right to look at the different, or the nucleophile, and see that because we have OK, this is an ionic bond, so we need to have O minus. O minus is going to be a strong nucleophile. We then have a bulk nucleophile. And so this is going to move toward E2. So if you remember from Justin's lecture, he said that for SN2, we do not like bulky nucleophiles because they get in the way of the backside attack. And so this is going to be called what we say is a bulky base, E2. What's special about the bulkiness of the base, though? Y'all remember? That was part of my lecture slides. Someone said Hoffman. That is correct. So we have two options for our hydrogen. Our neighboring hydrogens are here. Because this base is bulky, it's going to be slower if it interacts with the more substituted carbon. So for that reason, it's going to quickly interact with the less substituted carbon or the less substituted hydrogen. And so it's going to attack that hydrogen, make those go here, make this go here. We get this product. So this is the Hoffman product. All right. So we're just going to continue and we're going to do like, how many do I have after this? Quite a few. I'll do the next 3. No. Yeah, I'll do the next 3. And then I'll leave the remainders for y'all. All right, so this next one, I don't know if y'all have voted, but if you can, vote. All right, so the majority of y'all have chosen E2. And so that is because O minus, or OH minus, is a very strong base. And so we're going to put like strong base. And so it's going to be an E2 mechanism. It cannot be SN2. We have a strong nucleophile, but it can't be SN2 because this position is tertiary. Now, continuing through our E2 mechanism, we need to check for anti-coplanar. We actually don't have a illustration of what the chirality of this is, but remember it can rotate. What we can check, their chart of strong bases and strong nucleophiles. So there are, if you have access to, a lot of students have like an OChem Dropbox. There are different, and in the textbook, there are charts, but I would definitely emphasize learning your nucleophile trends, so learning how to tell yourself, because they can definitely throw anything at you, really. And if it's not one of the ones you've memorized, you may run into an issue. So memorizing that, typically if it has a negative charge, it's going to be a strong nucleophile. And then maybe differentiating between strong base and strong nucleophile, they are very synonymous. The only time that it really changes is like if you have sulfur minus or if you have phosphorus minus, that's a stronger nucleophile than it is a base. And that's because, remember, the basicity trends and stuff like that. But a lot of the times, just knowing your nucleophilic trends should get you pretty far. So I would focus on that. But anyways, we continue with the E2 mechanism. We know that we have to have the anti-coplanar. We know that we want to have the Hoffman product. And so the Hoffman product would This one is tricky. But the Hoffman product would prefer like the bulkier. Not Hoffman, I'm sorry, Zaitsev, you're correct. I'm sorry for my terminology lapse. Both of these do have two substituents. However, being on the ring is not going to be that great because this is a unique bond angle. And then furthermore, I believe that since this carbon has more inductive effects, we're going this way for our Zaitsev product. This one's tough. I don't think they would put this example purely on a test because it is tough. I would imagine they'd be a little more dramatic and have different substitutions in the end. But we will go to the right, and we are able to without rotating because we already have that dash orientation of our hydrogen. So our answer for this product is going to be that. All right. Moving next reaction, you can vote again. So first of all, it looks like some of y'all are changing your votes, but the first thing you should do is look at the nucleophile. We do not have a charge, we have an alcohol. Typically, our alcohols are going to be classified as weak nucleophiles because they don't have a charge. So if we have a weak nucleophile, then we're going to lean toward the one mechanisms, right? And then the reason why I did not go into the details on the electrophile for SN1 and E1 is again due to that fact that there is that competition. And so we're actually going to do E1, SN1. And again, they would specify on the test, or they plan to specify on the test, which product they're looking for. So this would only give elimination products, or it would tell you, give us the major elimination products. You'd still have to decide whether it's one or two, but they'll at least help you. You could say the big, it's kind of, I guess, bigger nucleophiles may lean toward E1, but I would say that since this is linear, yeah, so since this is linear, I would say you can definitely still do SN1. So removing the charge, you would need to be like in basic conditions. So they will tell you that O minus by giving you O and A. You only remove it when it's ionic. So unless your professors have been stressing like basic conditions or like workups, from what I could tell, I think in the past, we've treated stuff like alcohols as SN1, E1 reagents. So, and you can see that on the different practice tests that they'll give you. That trend follows in their answer keys. I guess they would need to specify something else underneath the arrow, like a base or something that might be able to abstract. But then that gets kind of confusing because then the base itself might be able to be a nucleophile. So in the past, my experience with OChem and the other semesters that they've taught, OH has been considered a permanent alcohol. You don't deprotonate. You would deprotonate OH if you had like sodium hydride. So that's a whole different reaction, and that would be converting OH into a nucleophile, and that's a separate, unique reaction that they could choose to know. Does that make sense? Overall, don't deprotonate alcohol. I would say that that's majorly true. Again, I haven't been in your classes, so cannot say 100% confidence that they can't negative charge if it gets ionized. So NaOH, yes, that already, so sodium plus OH minus is already OH minus. That's not a covalent bond. This, however, is a covalent compound. That's what it looks like. And so this is not charged, whereas this one is charged. If they gave you a base, I cannot see where they would want you to take this OH minus and then go and take away that hydrogen and make this minus, because it might, like, the OH minus would rather just attack directly. Does that make sense? And so for these reasons, again, unless they've been stressing hardly in lecture, I should not be expecting y'all to deprotonate. Covalent compounds don't split up. Yeah, pretty much. But you do have to remember there is that sodium hydride. So when you have something like this, where you have that intramolecular reaction, this converts it into O minus, which then attacks. So this is a whole separate reaction. But that's when they wouldn't give you a nucleophile. All right. Cool. We're going to choose the E1 and SN1 products. And because they, again, haven't specified, we are going to get a mixture of both. I'm going to show both of them. So if we had, the first step always is our leaving group leaving. So let's make sure we draw that. Then I will say, this is getting a little advanced, but I'm going to put, I'm not going to indicate stereochemistry right here, because you need to remember that you do get the racemic mixture of products with SN1, and then you don't get, okay, thank you, but you don't get stereochemistry on a double bond. So when you have a positive charge, technically this is sp2 hybridized, and so there is no there's no chirality, and then it loses its wedge and dash. But that's just very nitpicky intro step or intermediate step. We're going to continue. Let's do SN1 in this direction. Change colors. E1 in this direction. So E1, if you remember, it doesn't need anticoplanar because we already have this positive charge here. And so all we're doing is taking away hydrogen adjacent, and then we want to follow the Zaitsev rule. First, we've confirmed this is a tertiary carbocation, so it likely will not resonate or rearrange because it's already favorable. It will not change. So there's no rearrangement. And so elimination would come and take away this hydrogen, moving the bond down. We get that product. SN1, though, is going to attack directly. And we are going to get right. They may indicate chirality, I'll say that again, on an answer, but it is like plus an enantiomer. So in the past, I haven't indicated chirality on like rings and stuff, just because it's both. So that, in my opinion, is a mixture of both. But it is multiple choice, so you're just going to choose the answers they give you. That's our E1 or SN1 product. Y'all have any questions? No? All right. I'm going to move one further. This last one I'm going to do pretty quickly. This is just heat. And so if they just give you something like heat and nothing else, you need to look for an intermolecular reaction. If they give you sodium hydride, they could also look for an intermolecular reaction. But NH2 is a nucleophile because it has this lone pair. And so what's going to happen is it's going to attack the bromine, do a ring closure. And then because it's a ring, we're going to have 2 dashes. So because this is a weak nucleophile, the heat is pretty much going to favor like the leaving group leaving. And then it won't rearrange in this case because it needs to attack at a site other than its own base. And so it's a little bit of a complex example. Again, we're just trying to give you some challenging ones so you'll be surprised if they come up with something like this on the exam. So this is the product. Does that make sense? I got 2 dashes because it's a bicyclic compound, and so it would be like an unfavorable geometry if one of these was going up and one of these is going down, because then you have like a twisted picture. This is this SN2. So I would say that it's SN1. I think just because I think this is a weak nucleophile. So if this was N minus, heat alone forces bromine to leave. Yes, I would say because it's secondary, it's semi-stable. Heat would make that bromine leave. Heat drives reaction. Yep. And then just because this isn't a strong nucleophile, this is like neutral, and it's nitrogen. There's a carbocation. Yeah, I did put that carbocation there. Heat was better for elimination. So that is something that they said the book kind of tells you that, but it's hard to specify that again. In reality, even if you heat a reaction mixture, you'll still get a mixture of E1. And then furthermore, you can't really do an elimination on this ring because that would require it taking away a hydrogen from here or here. And so this is a unique reaction. And then again, I was told that they can put a heat symbol under any arrow, and that does not necessarily mean that it will only go elimination. So, but again, for E2 and SN2, the rules are rather more set. The only time that heat favors elimination, how we've thought, is through the E1 SN1 competition, and they've said that they'll specify those. So in the end, they know more about OCHEM, and then there is some ambiguity with OCHEM, whether or not heat will always favor E1. So yeah, I will say, told that they expected to have the opportunity to put heat under any arrow, whether or not it's SN1 or E1. Again, they'll ask for the substitution product, or they'll ask for the elimination product, or they'll only give you one option. All right. So I'm going to leave the rest of these examples to y'all. You can look at the key, and it should tell you guys the mechanism for each, I believe. Or they're fairly not obvious, but for the simpler reactions. So I'm going to continue to the next problem. So number 9, proposed detailed mechanism. I'm going to leave that one for y'all as well, because we got about 10-15 minutes left. And 9 is just a standalone question. This is the H2SO4 mechanism. If you need to look back at it, you can look at my lecture slides. Y'all will do number 9 on your own as well. For number 10, we're going to provide a name for the following compounds. Make sure to indicate structural isomers. So this one I will do. I'm going to only do one example, and it will be the more complicated one, because if we can do this complicated one, then these two you should be able to do on your own. So what we're going to do is label the longest chain. Thank you. there's the longest chain, 1 through 8. And I started on the right-hand side because 1 is going to give us the lowest number of substituents. And it's also going to have number 1 as our alkene. So we then identify we've got a methyl. So this will be like 3 met is what I'm assuming, 6 chloro, and then we've got 3 alkenes. So we have 1, 3, 5 triene. So that's where we're piecing together these pieces. And so our main chain has 8. So we've got oct as our chain name. Then putting all these together, still following furthermore, we only have this one is mono. So we don't name substitution there. This one, however, is tri. And if we label priorities, we would give this one more priority, and then this one less priority. It's hard to draw too. But this has more weight eventually. It's carbon and then more carbons. So the main chain is the higher priority versus the methyl. The other one, we have a hydrogen over here. And so carbon wins. And so this conformation is actually E, because the ones are on opposite sides. Then we've got our next double bond. That one is also tri-substituted, so we do have an E or Z nomenclature. Again, we've got a competition between a carbon and a hydrogen, so this is number 1 again. And then chlorine versus carbon, chlorine wins. So chlorine's number 1, and then this is number 2. So this one is going to be Z. Do you have any questions on those? All right, so putting all this together, it's a little tough. Instead of writing it all out, I'm going to choose to type it. So we put green. I'm going to do something blue. So we are going to have 3, 5Z. Oh, whoops. 5Z. So those are indicating, and those come at the beginning. Our orientations about the double bonds. And then we have to go alphabetical order. So chlorine is first. We're going to have 6 chloro. Next, we're going to have methyl. That's because triene, it comes at the end, but M is also our next alphabet. 3-methyl. And then we're going to do octa, and this is not Capson's real name, but I'm trying to specify that that's our chain. Octa, and this is going to be 1, 3, 5 triene. Do y'all have any questions on that name? I know it's a little tricky, but it's a great example because it gives all of the rules for naming alkenes. It gives the EZ nomenclature, and then it gives the diene, triene, tetraene. All right, doesn't look like you all have questions. So I'm going to continue to 11. Label each as Z or neither. All right, so I'm going to do the top row, leave the bottom row for y'all. So we draw a line through our double bond, and then we look at our substituents. In this case, we have hydrogens, and so we've got 1 and 1 as our carbons. And since they are on Actually, I am sorry. Where will the key be posted? When will, all right, when and where? So they have to edit this video and then they'll post it on YouTube. And I imagine that the key will be linked underneath the YouTube video for others to get it, or they may even email it to you guys directly since you guys actually showed up. So look for your email or periodically check the peer tutoring YouTube. So this one actually isn't either. So I actually started going down the wrong method, but this is only because it is die substituted. I'll redraw it to show. We only have two substituents, so this is trans. It's not E, it's not Z, it's trans. I hope that makes sense. For this next one, we separate the sides. We look at the molecule, so iodine is heavier and bromine's heavier. So because we have both on the same side, Z. We then look at this last one. Of the two, bromine is heavier. And then this is a little tricky, but this carbon we say is bound to 3 carbons for our counting purposes. And then this carbon is only bound to 2 carbons and 1 hydrogen. So this first carbon has more weight is how we think of it. But if you were doing chirality, you would also rank it the same. I hope that y'all would. But this is the proper way to rank them. And so this is also Z because it's on the same side. Any questions on those 3? Okay. Synthesis is definitely unique. I'm going to try and do maybe just one example because they can show up on your exam. We were told that simple synthesis, ones that are like 1 or 2 steps, can show up on your exam. And I think one of the ways that they imagined it could be, they could have a bank, like lettered A through Z, or however big they want to make the bank. Hopefully it's not A through Z, but they could just choose a bunch of different reactants, and y'all could choose the proper order. So I know it seems intimidating, but it definitely helps to practice these. There won't be many of those questions, I'll tell you, but that could show up on your exam. So that's why I want to leave more of these for y'all, and I'm just going to do one of them. So usually with synthesis questions, you'll do these in OChem 1 and OChem 2, is we're just looking at our product, and we identify differences. We obviously see there's a double bond here, and that's really our only difference. We don't have anything added anywhere else. And yeah, so how are we going to get a double bond? What do y'all think from what we've done this unit? Elimination. Yep, so eliminations form double bonds. How are we going to eliminate? We have to brominate first. That's a great instinct. A lot of your synthesis questions this semester could involve bromination first. I would definitely choose bromination probably over chlorination because you can't control chlorination. We need a leaving group. Currently, we only have carbons. Carbons are horrible leaving groups. So if we add bromine, first of all, it will add right here, correct? This is the most stable site. We would get our bromine here. So now, what's the difference between this intermediate and our product? Can we get there in one step? Add a strong base, yeah. So we add a strong base. However, what is unique about this product? We've got 2 options with every elimination reaction, right? The Zaitsev product, we've got the Hofmann product. So looking at this, we need an anticoplanar, yep. It needs to be anticoplanar, but we have the Hofmann product here. I hope you can see that the relationship here is Hofmann. It's an A. Hofmann, because it's the less substituted. More substituted would be if the double bond was here. So how do we get the Hofmann product? The Hofmann product does need a bulky base. If you remember, E1 is almost always going to get our Zaitsev product. We can rearrange. We're going to do E2. We're going to use a bulky base. So and that would be the completed synthesis. Does that make sense? It's an O minus Na plus. We've got a strong bulky base, O-butyl, and it's going to force the Hofmann product to form that double bond there. I hope y'all learned something from that logic. These other questions will definitely be valuable for y'all to practice on. And then it is 1 o'clock, so the final problem is a roadmap problem. This also could show up on your test. This is a long roadmap. We'll make it E1. So for synthesis, one rule of thumb is I would stay away from the 1 reactions if you could, because you can't control them. Remember, you get a mixture of SM1 and E1. And then with SM1, you don't control chirality either. So a lot of these are not controllable. You can do, like there are instances where I guess SM1 or E1 could be available, but a lot of times if you're doing synthesis, I would imagine it rely heavily on SM2 and E2 because y'all can definitely control those and say, without doubt, the only product of this reaction is going to be the product that I want. Anyways, this last question I'll leave for y'all too. This is a roadmap. So I actually specified here E2 for the roadmap. They may do that because technically we do have a secondary carbon. You can examine this yourself, but there are reasons for every one of these reactions. So with that, I think it is 1 o'clock, so we are done. This is really helpful. Thank you. Yeah, we're happy to help. Again, you can find this recording and watch it again, or at least do the problems and then compare it to the key. But y'all are going to do great. Don't stress. Yep, y'all have a great day.